Section 1 Introduction. Let's dive right into it. Over time, we've seen an incredible evolution in the performance of pre-trained large language models, or LLMs, as we'll call them. They've made the leap from being good at specific tasks to now being highly proficient at more general tasks if they're provided with the right instructions. This impressive advancement is largely due to the increase in the scale of training data and the number of parameters used. Lately, the focus has been on creating smaller models trained with a greater amount of data, which are easier to handle when it comes to making predictions or inferences. A perfect example of this is the Llama model. It's a relatively smaller model with 7 billion parameters, trained on a whopping 1 trillion tokens, yet its performance is almost on par with that of the larger GPT-3 model, despite being 25 times smaller. There are techniques available that can reduce the size of these models even further, up to about 4 times smaller. The exciting part is that this drastic size reduction doesn't compromise the performance of the models. Instead, these compact versions can perform just as well as the largest GPT-3 model, while requiring much less memory. This kind of improvement means that high-performing models could be efficiently used directly on devices like laptops. However, the real challenge lies in achieving enough model compression to fit on these devices without sacrificing the quality of the generated output. We've learned from various studies that despite their precision, the current techniques for 3 to 4-bit quantization tend to lead to a significant drop in accuracy. Since LLMs generate predictions sequentially, based on previously generated tokens, even small errors can add up over time, leading to considerably corrupted outputs. This is why it's vital to come up with a low bit width quantization technique that can preserve the predictive performance of the original 16-bit model. Our solution to this challenge is the introduction of what we call Sparse-Quantized Representations, or SpQR. This is a hybrid sparse-quantized format that can reduce the size of an accurate pre-trained LLM to just 3 to 4 bits per parameter without any significant loss in quality. Specifically, SpQR is the first weight quantization method that can achieve this level of compression while inducing less than a 1% error in end-to-end accuracy compared to the dense baseline. SpQR works by combining two key innovations. The first one is to separate out outlier weights, which we found to cause unusually high errors when quantized. These weights are kept at high precision, while the rest are stored in a much lower, for instance, 3-bit, format. Secondly, we use a variant of grouped quantization with very small group sizes. To transform a pre-trained LLM into SpQR format, we use an extended version of the post-training quantization method introduced by GPT-Q. Our method consists of 2 steps. First, we detect outlier weights that have a significant impact on the output behavior when quantized. Then we compress the rest of the weights to a lower bit width, extract the outliers, and further compress the quantization metadata to make the entire representation more efficient. Our approach is driven by a new analysis showing that LLM weight quantization errors are linked to both input feature dimensions and output hidden dimensions, exhibiting both vertical and horizontal group correlations. We are the first to show that similar outliers occur in the weights for particular output hidden dimensions. These outliers occur only in small segments for a specific output hidden dimension. To make the most out of this structure, we've developed a specialized sparse matrix multiplication algorithm based on the compressed sparse row format. To use SpQR for generating predictions token by token, we combine this sparse algorithm with a dense quantized matrix multiplication for 3 to 4-bit weights. Ultimately, using SpQR can reduce the memory footprint of LLMs by a factor of about 3.4x or more without any loss in accuracy. It is also 20 to 30% faster in generating predictions compared to 16-bit inference. This novel method allows us to exploit the power of large language models more efficiently and practically on smaller devices. Section summary. The trend in language model development has shifted towards smaller models trained on more data, which are easier to use at inference time. However, compressing models to fit on end-user devices while preserving generative quality remains a challenge. Sparse-Quantized Representations, SpQR, is a hybrid sparse-quantized format that can compress accurate pre-trained language models to 3 to 4 bits per parameter while staying near-lossless, reducing memory footprint by a factor of about 3.4x or more without degradation in accuracy, and being 20 to 30% faster for language model generation compared to 16-bit inference. Section 2 Related Work. We're going to discuss the related work in the area of post-training quantization methods, which are effective techniques to compress models of various sizes in one go, using only a limited amount of calibration data. For a deeper dive into quantization, we recommend referring to the detailed survey by Golami and colleagues. Post-training quantization methods, such as ADA-round, bit-split, ADA-quant, BRECQ, or OBQ, have been primarily designed for vision models or smaller language models, those with less than 100 million parameters. These methods rely on precise solvers and are commonly used to address layer-based or group-based compression problems. However, these methods may not be scalable to models as large as GPT, as their computational or memory costs would be prohibitively high due to the fact that such models are between 10 to 1,000 times larger. Recently, there has been increased interest in developing accurate post-training methods that can accommodate such massive models. Early work in this area, like zero-quant, LLM, Int8, and NUQMM, used a straightforward approach, rounding off weights to the nearest quantization level and adjusting the granularity of quantization to balance storage space and precision. LLM. Int8 also suggested treating outlier features differently, quantizing them to a higher bit width. These methods succeeded in maintaining relatively low quantization errors, with an example being a mere 5.5% increase in language model loss for a 7 billion parameter llama model at 4-bit weight quantization, assuming sufficiently low quantization granularity. A more accurate approach, like GPT-Q, proposed the use of an approximate large-scale solver to minimize layer-wise squared errors, resulting in an even lower loss increase of 4% under the same conditions. An in-depth analysis by Detmers and colleagues of the trade-offs between accuracy and compression underscored that 4-bit quantization was optimal for these rounding-based methods. They also pointed out that data-aware methods such as GPT-Q could achieve higher compression levels. Sparse-GPT offered a method to sparsify LLM weights while also quantizing the remaining weights to a fixed bit width. However, a shared downside across these methods was a substantial loss in accuracy compared to the original model. This is particularly relevant for small, deployable models with 7 to 13 billion parameters, where current methods lead to considerable accuracy drops. We're exploring this issue and are proposing a new compression format that can achieve near-lossless compression with just 3 to 4 bits in this range. Also of interest is the simultaneous quantization of both activations and weights. Preliminary work has shown that it's feasible to quantize both these elements to 8 bits with minimal impact on accuracy. Such studies provide valuable insights into the reasons for compression errors in large language models. We observe that outlier features, with notably higher values in the input-output of large language models, introduce higher quantization errors. We're examining this issue from the perspective of weight quantization, and particularly investigating the structure of these outliers in the weight matrix. We've found that while there's a correlation between outliers in the current layer and outliers in the previous layer's weights, the relationship isn't direct. This suggests the need for a hybrid compression format that's more sophisticated than those exploiting the column structure of outlier features, as previous research has done. Hybrid sparse-quantized formats have been examined for deep networks. For example, some CPU-based inference engines support a format where each block of 4 weights is either completely sparse or quantized to 8-bit. On the other hand, GPUs support a format where each group of 4 weights includes 2 zero weights and the non-zero weights are quantized. The FBGEMM package proposed a format where certain outlier weights are quantized separately to lessen their effect on normalization. However, in this format, outlier weights are still quantized to the same 8-bit width as regular weights, and there's no clear procedure for post-training conversion to this format. We differentiate ourselves by 1. Offering an effective and accurate post-training compression algorithm that recognizes outliers as weights causing high output errors. 2. Suggesting a format that compresses outliers to a higher bit width relative to regular weights. And 3. Organizing outliers in blocks, allowing for efficient implementation of GPU kernels, which we provide. Section Summary. The section discusses related post-training quantization, PTQ, methods, which are used for one-shot compression of models with limited calibration data. Most PTQ methods were designed for vision models or small-scale language models, with less than 100 M parameters, and use accurate solvers that do not scale to GPT-scale models. The section proposes a new compression format that can lead to near-lossless 3 to 4 bits compression in the 7 to 13 B parameter range, and investigates the causes of compression error in the case of LLMs, specifically the presence of outlier features that induce higher quantization error. The proposed format compresses outliers to a higher bit width relative to regular weights and stores them in blocks for efficient implementation of GPU kernels. Section 3. Quantization sensitivity of LLM weights. In Section 3, we discuss the sensitivity of local linear models, LLMs, to quantization, focusing first on parameter sensitivity under this process. Not all elements in a neural network carry the same level of importance. To understand this, consider a weight that is highly sensitive to quantization. This is a weight with a large rounding error, meaning it's not closely aligned with a quantization point, or a weight that's often multiplied with a large input, thereby making even minor rounding errors quite significant. However, this elementary understanding of sensitivity doesn't account for the complex functioning of LLMs, which handle extensive vectors with considerable correlations. For instance, a weight, W_A, might have a large rounding error, but it's strongly correlated with another weight, W_B. In such a case, the error from rounding up, W_A, can be effectively balanced by rounding down, W_B. This concept is harnessed by modern quantization algorithms, which can yield superior results over basic rounding, especially at low bit widths. To address this complexity, we need a more comprehensive definition of sensitivity. For practical purposes, we gauge sensitivity on a layer-by-layer basis using a small collection of calibration inputs X, which are processed through the model up to the particular layer. The sensitivity, S_ij, of a weight, W_ij, in the layer's weight matrix W is defined as the minimum squared difference between the original predictions on X and the predictions of any weight matrix W_prime in which this weight is quantized. Importantly, all weights of W_prime, except for W_prime_ij, can adopt arbitrary values, quantized or not, to make up for the quantization error that results from rounding, W_ij. This encapsulates the aspect of correlation we previously discussed. Also, since we allow continuous values, this problem has a direct solution. It can be derived following the generalized optimal brain surgeon framework, where the inverse Hessian matrix corresponds to the optimization problem. An effective approximation of this sensitivity measure can be accomplished by quantization solvers like GPTQ. Specifically, GPTQ quantizes weight matrices column by column, while adjusting the yet-to-be quantized section to account for the quantization error in a manner similar to our previous definition. As a result, sensitivities aren't determined all at once but are computed dynamically as the algorithm processes each column, using the inverse of the Hessian subselection corresponding to all not yet quantized weights. This matrix is efficiently computed by GPTQ, adding no extra computational burdens. A key advantage of this method is that S_ij is always calculated based on the most up-to-date value of W_ij, allowing for adjustments due to previously quantized weights. Section summary. The sensitivity of weights to quantization in neural networks is not solely based on their rounding error and input amplification, but also on their correlation with other weights. A more robust definition of sensitivity is required, which can be assessed on a per-layer level using a small set of calibration inputs. The sensitivity of a weight can be determined using a closed-form solution based on the inverse Hessian matrix, and can be approximated efficiently by quantization solvers such as GPTQ. Section 3.2 Exploring Parameter Sensitivity. In this section titled, Exploring Parameter Sensitivity, we begin to lay the groundwork for our primary method, SpQR. By taking a closer look at how sensitive certain weights are in the model's weight matrix. Interestingly, we found that these sensitive weights don't appear haphazardly, but are instead part of unique structures. Using the highly regarded Llama 65B model, we analyzed each individual weight for sensitivity. We then presented this data visually to highlight the distinct structures within the weight matrix. To achieve this, we employed GPTQ quantization to 3-bit, which is a quantization method that doesn't require weight grouping. We evaluated the error based on 128 sequences, each containing 2048 tokens, taken from a calibration dataset. We noticed various patterns within the weight matrix of the final self-attention layer of the Llama 65B model, with some patterns restricted to a single row or column. Because of the enormity of the weight matrices in Llama 65B, we used max pooling to help visualize the matrix by selecting the maximum sensitivity within each 32 by 32 row and column square. This process only affected the leftmost image. The visualization unveiled a layer-dependent and depth-dependent variation in quantization error patterns. For example, we noted a difference in patterns between attention layers and multilayer perceptron (MLP) layers. Moreover, deeper layers seem to have more highly sensitive outliers. By analyzing the attention weight matrix, we were able to categorize different outlier structures. For instance, row outliers are highlighted as areas of high sensitivity within one output unit, with some patterns spanning an entire row. Similarly, column outliers, which showed high sensitivity across all rows for selected input dimensions, seem to be related to the outlier feature phenomenon previously noted. Furthermore, we noticed certain attention heads marked by consistent stripes of width 128, indicating these heads may hold more critical functions. Within these sensitive heads, the sensitivity of individual weights still varied greatly. This striping pattern was horizontal for attention Q and K projections, vertical for output projections, but was absent from value projections and MLP weights. We also noted the rotary embedding pattern, a vertical sensitivity pattern that repeats every 64 units. This likely results from the use of rotary embeddings, where each attention head is divided into two parts, the first 64 using cosine rotation, and the other 64 using sine rotation, both employing the same set of frequencies. We found that weights corresponding to lower frequency sines and cosines were generally more sensitive compared to those with higher frequencies. This pattern was missing in layers not employing rotary embeddings. Finally, we came across outliers that did not fit into any of the previous patterns. These unstructured outliers appeared more frequently in columns with the largest input index, which was challenging to visualize on a heat map. We believe this is an artifact of the GPTQ algorithm, which compresses weights one at a time, using uncompressed weights to compensate for any errors. As a result, the final batch of weights on the rightmost side of the image accumulates the most errors. We'll use these findings to develop a compressed representation that can handle all the various types of outliers we've identified. Section summary. The authors explore parameter sensitivity in the weight matrix of the Llama 65B model and find that sensitive weights have particular structures, such as row and column outliers, sensitive attention heads, rotary embedding patterns, and unstructured outliers. They use GPTQ quantization to 3-bit and perform max pooling to visualize the matrices, observing that quantization error patterns vary by layer type and depth. They propose a compressed representation to support all these different outlier types. Section 4.1 Overview. In Section 4.1, we're proposing a novel approach to handle the limitations seen in existing low-level memory, LLM, quantization algorithms. Typically, these algorithms don't discriminate between weights of low and high sensitivity. We've found that this can result in less than ideal quantization. In our method, we prefer to allocate more of the size budget to weights that are more sensitive. However, these sensitive weights are scattered throughout the weight matrix, either as isolated weights or small clusters such as parts of rows or attention heads. We're proposing two key modifications to the quantization procedure to accommodate these, one for identifying small sensitive groups, and another for pinpointing individual outliers. We have seen situations where weights behave alike in small consecutive groups, but with sudden changes between these groups. Under standard procedures, these weights often end up grouped together and sharing the same quantization characteristics. To lessen this, we employ group-wise quantization, focusing on very small groups, typically made up of 8 to 32 weights. Here, each group of consecutive weights has its unique quantization scale and 0 point. This is somewhat counterintuitive to recent beliefs that small groups would incur too much overhead for storing quantization statistics, negating the precision benefits. However, we mitigate this issue by also quantizing the group-wise statistics using the same method as for weights, asymmetric, or min-max, quantization. This ensures the range of quantized values will adapt to the groups with the most extreme quantization scales, achieving perfect quantization. We then bundle the group-wise statistics from 16 consecutive values and quantize them together in the same number of bits. Groups with unusual quantization parameters thus use more of the quantization budget. Both first and second level quantization occurs within the process, allowing the algorithm to compensate for second level quantization errors. There are instances where a small percentage of sensitive weights appear as small groups or individual outliers, causing a disproportionately high quantization error. In such situations, we prefer to maintain these outliers in high precision, 16-bit. These outliers, often unstructured, are individually encoded in a row-wise format, akin to a compressed sparse row, CSR, representation. This can accommodate both individual outliers and small structures not fitting into the prior group definitions. To detect outliers, we use a two-step process. 1. Find and isolate outliers as 16-bit weights, and 2. Quantize the non-outlier base weights into 3 to 4-bit and transfer the remaining quantization into the 16-bit outliers weights. We use a filtering technique based on a sensitivity criterion to separate outliers from base weights. For each matrix, our aim is to select a sensitivity threshold to obtain the desired number of outliers across the whole model, typically around 1% of weights. A weight is considered an outlier if retaining it in 16-bit decreases the error by at least the chosen threshold. After this initial outlier detection step, we quantize the base weights ignoring all outliers in the same quantization group. The quantization statistics are computed excluding outliers, leading to notable improvements in error. Subsequently, we apply GPTQ to quantize the remaining weights. Intriguingly, a weight can be deemed an outlier not only if it generates error individually but also if it can be used by the GPTQ algorithm to offset errors from other weights. Finally, We collect and compress the sparse outlier matrix as well as the final quantization statistics using bi-level quantization. This gives us compressed weights and their metadata. For optimization, our algorithm also includes several features. For instance, with small group sizes, it's common for a group to consist entirely of positive or negative values. If we do away with the requirement for maximum values to be positive and minimum values to be negative, we find a slight improvement in quality. Additionally, our algorithm accommodates non-integer 0 points as a result of quantizing the quantization statistics. We'll further elaborate on these and other components of our algorithm in the following section. Section Summary. The authors propose a new quantization algorithm, sparsity-aware quantization with outlier removal, SpQR, that assigns more of its size budget to sensitive weights. They introduce two changes to the quantization procedure, one for capturing small sensitive groups and another for capturing individual outliers. The algorithm also contains several optimizations, including non-integer 0 points and the removal of the requirement for the maximum value to be positive and the minimum value to be negative for small group sizes. Section 4.2 Implementing and Leveraging the Sparse-Quantized Representation. In Section 4.2, we discuss our method for creating and utilizing the Sparse-Quantized Representation, SpQR. This approach involves transforming homogeneous weights into multiple data structures of various sizes and accuracies. In general, our SpQR is composed of three main elements: 1. Quantized weights. 2. First and second level quantization statistics. 3. The indices and values of CSR outliers. The overall structure of SpQR is illustrated in a figure in the original paper, but we'll describe each component in detail here. Firstly, all weights, excluding the outliers, are stored in a structure that includes a specific number of bits for the individual weight, a specific number of bits for the scale and 0 point for each group, and 16-bit statistics for quantizing groups of a certain size. Let's break this down with a specific example. Suppose we have the same number of bits, 3, for the individual weight and for the scale and 0 point, and groups of 16. The weight matrix is then divided into groups of 256 weights. Each group contains 256 individual 3-bit codes. For every 16 weights, a separate 3-bit scale and 0 point is used. Finally, there are 4 16-bit values for the entire group, used for second-level quantization. For efficient GPU memory access, we adjust the 16-bit versions to accommodate the quantized values for outlier weights. Both quantized weights and quantization statistics are stored contiguously in memory for each group. This layout could be further optimized for different hardware, like mobile CPUs, by eliminating the quantized version of outliers, an avenue we're considering for future research. The outlier values in our system are unstructured, and we store them by sorting first by row, then by column. This ensures that outliers within the same row are stored contiguously in memory. For each outlier, we store two 16-bit values, the weight and the column index. Additionally, for each row, we store a 32-bit number representing the cumulative count of outliers up to that row. This setup results in an average storage cost of about 32 bits per sensitive weight. The efficiency could be significantly improved by grouping outliers, which is another area of future investigation. We've also designed an efficient GPU-based decoding implementation for SpQR, aimed at popular use cases like token-by-token language model, LLM, generation. Because autoregressive inference on GPUs is memory-bound, high compression rates can somewhat mask the overheads of decoding. Broadly, our algorithm first loads group statistics and quantized weights into shared memory. It then dequantizes these values to 16 bits and performs matrix multiplication using 16-bit inputs. To handle outliers, we've created a sparse matrix algorithm that capitalizes on the row occurrence of outliers. The algorithm works by dividing the matrix into equal size blocks, with each GPU core loading a slice of outliers into shared memory. The cores then determine which outliers are part of their segment. The corresponding weights are loaded from the main memory, and then the matrix multiplication is performed. This process essentially balances the load in the first 3 steps, while the last step tends to access memory contiguously due to the row-like pattern of outliers. As we'll show in the following section, this tailored approach is quicker than the sparse matrix algorithms available in PyTorch. Section Summary. The SpQR algorithm converts homogeneous weights into various data structures of different sizes and precisions, including quantized weights, quantization statistics, and CSR outlier indices and values. The algorithm stores quantized groups and outliers in contiguous memory regions, and uses a GPU-based decoding implementation for efficient inference. leveraging autoregressive inference and a sparse matrix algorithm that takes advantage of outliers occurring in rows. Section: Experimental Setup. In our study, we focus on three main objectives. First, we're interested in finding the smallest possible model that SpQR can use to replicate the performance of a 16-bit model within a margin of just 1% in terms of perplexity. Second, we want to compare the performance of SpQR with other methods while maintaining a consistent average number of bits per parameter. In this context, we'll compare it to the round to nearest and GPTQ baselines. Lastly, we're aiming to identify the ideal balance between the size of the model and its performance. To carry out our evaluations, we use the full SpQR algorithm on publicly accessible large language models, specifically focusing on the Llama 7, 13, 30, 65B and Falcon 7, 40B model families. For these models, we applied quantization using the Red Pajama dataset for Llama and the refined Web dataset for Falcon models. These datasets are public duplicates of the original training data for these respective models. In addition to SpQR, we also compared the results against two other post-training quantization strategies, GPTQ and simple round to nearest RTN quantization. Most language model compression methods use this RTN technique. Both of these baseline methods use 4-bit quantization, which offers an optimal balance between quality and size. However, with SpQR, we used both 3-bit and 4-bit base quantization. The resulting model size might be a bit larger due to the presence of outliers. We used two metrics to evaluate the performance of the quantized models. First, we measured the perplexity, using the Wikitext2 and Penn Treebank datasets. Second, we assessed zero-shot accuracy on 5 tasks: Wino Grande, PIQA, Hella Swag, Arc Easy, and Arc Challenge, using the language model evaluation harness with recommended parameters. Our work took roughly 4.5 hours for the largest model size, 65B, on an NVIDIA A100, and about 6 hours on an A6000. We maintained the same model size for the RTN and GPTQ by using a 4-bit base quantization. For SpQR, we used a 3-bit base quantization, a group size of 8 for the first quantization, a group size of 64 for the second, and included as many outliers as possible while ensuring we still had fewer than 4 bits per parameter on average. Our goal was to achieve near-lossless compression, which we defined in line with the ML Commons benchmark, a 1% error relative to the uncompressed baseline. In all our SpQR evaluations, we adjusted our threshold, tau, to ensure the proportion of outliers stayed below 1%. Section Summary. The experimental setup focuses on evaluating the SpQR algorithm's performance in 3 main settings, including compact representation, average number of bits per parameter, and the best trade-off between model size and performance. The SpQR algorithm is compared against two other post-training quantization schemes, GPTQ and simple rounding to nearest RTN quantization, using 4-bit quantization. The evaluation is based on perplexity and zero-shot accuracy metrics on publicly available LLMs, and SpQR's implementation takes around 4.5 hours on the largest model size, 65B, on an NVIDIA A100 and about 6 on an A6000. Section: Main Results. Let's delve into our main findings. We put our focus on examining the relation between the actual size of our models, perplexity on Wikitext2, and accuracy on tasks performed without any prior training. Our observations were quite fascinating. The SpQR technique displayed superior performance over both GPTQ and, subsequently, RTN when it came to comparable model sizes. The margin of this improvement was quite noticeable, especially in the case of smaller models. This enhanced performance can be attributed to two major factors. Firstly, SpQR was able to compress the models more effectively, and secondly, it minimized the loss degradation. To dig a little deeper, we quantified the number of bits needed for each parameter to get within a 1% deviation from the performance of 16-bit models in terms of perplexity. Here again, SpQR stood out. We found that with merely 4.6 to 4.71 bits allocated to each parameter, SpQR could replicate the performance of non-quantized models, deviating by no more than a 1% margin of error across all models. For those seeking exact values, we've included these in our tables. Continuing with our analysis, we maintained the model size constant and compared the performance of SpQR and other baseline methods, all using 4 bits per parameter. We used two sets of models for this analysis, the Llama and the Falcon family models. Our results consistently showed SpQR performing better than the other methods we compared it with. Interestingly, the difference in performance between SpQR and the next best method, GPTQ, was as pronounced as the gap between GPTQ and the less effective RTN. In summary, when using 4-bit parameters, SpQR managed to cut the error rate in half relative to the 16-bit baseline, a feat that GPTQ could not match. Section summary. The study compares SpQR and GPTQ models on Llama and Falcon family models. The results show that SpQR outperforms GPTQ in terms of compression and loss degradation, especially on smaller models. SpQR also achieves a 1% margin of error for all models with 4.6 to 4.71 bits per parameter, while GPTQ only achieves this with 5.5 bits per parameter. Section: Ablations. In this section, we explore a technique called SpQR and its distinctive features: two-level quantization with small quantization group sizes, and the use of unstructured outliers. First, we compare the impact of using different group sizes on performance. Specifically, we contrast the results from a 3-bit SpQR with a group size of 16 against a setup with a group size of 48, both using a 2-level 3-bit quantization method. Both setups yield an average of 3.6 bits per parameter. We don't use outliers for either of these setups for the sake of simplicity. In the accompanying table, the term 3-bit statistics refers to a group size of 16 with 3-bit statistics, and 16-bit statistics signifies a group size of 16 with 16-bit statistics. Interestingly, we found that despite the same, or slightly smaller, memory footprint, the use of quantized statistics significantly enhanced the language modeling loss. Next, we question the necessity of using unstructured outliers. For this, we compare two types of outliers. First, we apply the method proposed by Detmers et al. To identify column outliers and quantize them at a higher precision. Alternatively, we consider entire rows, like output units or neurons, as outliers. This involves running SpQR without outliers initially, then selecting k output units with the highest quantization error, mean square error between layer predictions, and treating those entire rows as 16-bit outliers. We compared these three types of outliers using 3-bit SpQR. Our results showed that unstructured outliers help reduce perplexity notably quicker than row outliers or the Detmers et al. Criterion, even after accounting for different memory footprints. We also examined how minor changes in hyperparameters, which we introduced at the end of the previous section, impact results. Without these changes, the round 0 entry represents a SpQR variant where the 0 point is a 3-bit integer. This reduces SpQR's memory footprint, but leads to a moderate increase in perplexity. We also tested SpQR without the act order flag. This option rearranges the input dimensions according to the diagonal of the inverse Hessian, a feature of the GPTQ algorithm. While this tweak slightly improved loss, it wasn't as effective as using quantized groups. In summary, both smaller quantized groups and unstructured outliers significantly improve perplexity and outperform other strategies. SpQR also benefits from using the GPTQ activation order heuristic, though the improvement is less substantial than from outliers or small groups. Nevertheless, we chose to use the same activation order heuristic in the GPTQ baselines for a fair comparison. For a more detailed exploration of SpQR's design parameters, we have provided an additional hyperparameter study in the appendix. Section summary. The SpQR representation differs from standard quantization methods in two ways: by level quantization with small quantization group size and unstructured outliers. Using quantized statistics significantly improves language modeling loss. Unstructured outliers reduce perplexity significantly faster than their row counterpart and the criterion of, even after accounting for the different memory footprint. Both small quantized groups and unstructured outliers independently improve perplexity and perform better than alternative strategies. Section: Inference time. We're going to look at the speed of SpQR, a method we developed during the process of inference. Our primary aim is to gauge the time it takes for this system to generate tokens, specifically when the workload is limited to a single A100 GPU and a batch size of 1. We examine the inference speed under two circumstances. First, we measure how long it takes for the system to generate 100 tokens from the beginning. Second, we assess how long it takes to add 100 tokens to a pre-existing 1024 token prompt. Our examination takes into account our specifically designed sparse matrix multiplication algorithm, comparing it with the existing algorithm in PyTorch, known as QSparse. We also include a comparison with a 16-bit baseline for reference. Our measurement criterion is the inference steps per second for the entire SpQR process, including both the dense and sparse multiplication parts. Our findings, detailed in the provided table, show that PyTorch's standard sparse matrix multiplication doesn't outpace the 16-bit inference. However, our tailored sparse matrix multiplication algorithm does improve speeds by roughly 20 to 30%. We also discuss and identify the constraints of SpQR. Our method, which applies higher precision to significant outliers, achieves near-lossless 16-bit accuracy with less than 4.75 bits per parameter on average. This offers a better balance between quality and size, especially when compressed to as little as 3.36 bits. This makes SpQR an ideal option for memory-constrained devices. Yet, we have some limitations. We haven't tested the generative quality of quantized language models, LLMs, focusing instead on predictive performance in terms of zero-shot accuracy and perplexity. Even though we think perplexity measures and generation quality are strongly interconnected, this is an assumption we plan to scrutinize in our future research. Furthermore, although we have developed a sparse matrix multiplication algorithm to quicken calculations involving outliers, we haven't fused this with the standard quantized matrix multiplication. Such a combination could further enhance the inference time performance. However, this is quite a challenging task to implement. Hence, we're leaving this aspect to our future research efforts. Section summary. The authors evaluate the inference speed of SpQR for autoregressive inference and compare their specialized sparse matrix multiplication algorithm with the algorithm implemented in PyTorch. They achieve speedups of about 20 to 30% and demonstrate that SpQR is an ideal method for compressing models for memory-limited devices. However, they do not evaluate the generative quality of quantized LLMs and do not fuse sparse matrix multiplication with regular quantized matrix multiplication, which could yield even better inference time performance.